Welcome to another FC480 video. Today I would like to take some time to discuss the concept of sampling distribution. According to our foreign discussion in the past 2 weeks, we seem to have more or less some misconception or confusion over the concept of sampling distribution. So sampling distribution means if I have a population, that's my underlying population. And then if I sample from this population time and time again until I exhausted all the possibility and then plug all the means together and then I form a new distribution. Will my new sampling distribution have the shape that depends on the underlying population distribution? The short answer is no. And today we're going to talk about the intuition behind that. Okay, so in order to tap on the intuition, I have prepared some simple simulation for us to see. We're going to first of all formulate a population distribution that's really not normal looking. We're going to go with the exponential distribution. And the reason I pick it is because I know exponential distribution is one of those distributions that's not normal looking. It looks like this. If you want to find out what it is, you can simply type in exponential distribution in the Google search and then just read the Wikipedia page. Okay, so we first simulate a population distribution. All right, take a look at this population. Right, it's definitely not normal looking, right? And then I'm only using the default setting, but we can take a look at the mean of this population is about 1. Standard deviation is about 0.9. Okay, you don't need to know why, but this is the standard deviation and the population standard deviation and population mean. Well, actually, this won't be the population standard deviation because whenever I use R command SD, it automatically returns the sample standard deviation. You may have to do something to correct it. But for now, we will say that it's approximately 0.9. All right, and then we will make an empty vector of 1,000 times. 1,000 times. Actually, let's make it to 10,000 times. Let's make a vector of 10,000 because we're going to do this sampling 1,000 times. All right. So let's set the sampling size to 4. So every time I'm going to pick from this population 4 sample. We're going to take a look at the sample. I sample 4 value from it. And then I'm going to compute the sample mean. All right, so the sample mean of this 4 value is, actually I should run this line. Okay, so the sample mean of my 4 values would be approximately 1. And I'm going to sample it 10,000 times. So here it goes. All right. And then let's take a look at our sampling distribution. It's not perfectly normal looking, but you can see that most of the value, within, you can easily see that there is a very obvious central tendency around this value. And if we take a mean, it's about 1, pretty close to the mean of the population, right? And the standard deviation is 0.4, which is approximately whatever that we had before, which is about 0.8 divided by 2, right? Because we have a size of 4. All right. And if I change this value to 10, will my sampling distribution look more normal? Well, actually, it does look more normal, right? If we keep increasing the sampling size, if we keep increasing the sampling size, let's see, let's do 30. Will it look more normal? I think it does, right? It gradually look more normal as we increase the sample size, right? Let's increase it to 90 and see what happens. Say that it looks fairly normal, right? But let's see that if we are sampling with if we sample with sampling size of 100, and we get this. And why? Because at this point, if we have a sampling size of 100, our sampling distribution is going to look like this. We pretty much will be getting the same value, right? Because according to law of large number, if you have a sample size that's fairly big, you pretty much hit your sample mean is going to be pretty close to your population mean anyway. So in the end, you're going to end up with a something of a straight line. You know, if you can pluck all the value, it's pretty constant. It's going to form a straight line. So you can imagine why this is happening, because your standard error essentially, so the standard error is the standard deviation of your sampling distribution, right? I hope you guys see that. If you don't know why, you should review your material. Why the standard error is the standard deviation of the sampling distribution. Right? So at this point, if you have a sample size that's this big, your sample error is going to be 0, which means that your distribution is pretty much a straight line. Or just imagine that, let's sketch this out. Right. So let's imagine that you have a, obviously cannot draw a straight line. So let's imagine this is your sampling distribution when your sample size is 4, right? And your sample size is 10. It's going to be a skinnier distribution, because your standard deviation is essentially getting smaller and smaller, right? And this is when you're using sample size of 30, let's say, 50, and then your distribution is actually going to be skinnier and skinnier. When it gets to the point that your distribution is so skinny that it's pretty much just a straight line. So that's what's happening here, right? Because your standard deviation, your standard error is essentially 0. So I guess my point is to tell you that in a way, actually not in a way, the sampling distribution, the shape of it is going to be independent from your population distribution. And as your sample size get large, yes, it's going to be looking more normal. But if you have a fairly big sampling size, instead of getting a normal distribution, you should be getting a constant, right? Which is pretty much a straight line. So hope you guys hope this is helpful in terms of sorting out your understanding of what the sampling distribution and what it does. Okay. I'll see you guys in the next